That syncs it up. 1.3, continuity in behavior and limits. We have continuity. The graph of a continuous function has no breaks, holes, or gaps. In other words, you can trace the graph of a continuous function without lifting your pencil. So you should be able to just graph it and never lift your pencil. If that's the case, this is a continuous function. To understand what it means for a function to be continuous from an algebraic perspective, it helps to examine the graphs of discontinuous functions, or functions that are not continuous. Functions can have many different types of discontinuity. So the first one we're going to look at is an infinite discontinuity. In other words, at some c, at some value, the graph is either going down as it gets closer to that c, or going up to infinity as it gets closer. So it's either going down to negative infinity or up to infinity. That's an infinite discontinuity. A jump discontinuity comes from piecewise functions. So the graph is going along, it's approaching this value down here, and then jumps up, and then continues on going from left to right. Jump discontinuity. Then if we have a hole in the graph, this is called a removable discontinuity. You could remove the discontinuity just by filling in that point. That's all it would take. Now the jump discontinuity, that's not a removable, because even if we filled that in, it's still not continuous now. A limit. The first time you've probably heard that word, a limit. A limit is a value a function approaches. It doesn't have to get there, it's just what is it approaching. So the first example we have is probably the most boring. This means the limit as x approaches 1 from the left, if you put a little minus there, of f of x is equal to whatever value we can come up with. So there should be a little, it should have printed nice, it's just not showing up on here. Should have a little minus there. Now that means, what is the function getting, what is the y value approaching as x gets closer to 1? And in this case, the y value the function is approaching is 2 to the left. The y value the function is approaching from the right is also happens to be 2. That won't always be the case, but in this one it is. Now, since the left hand and the right hand limit, since they equal each other, the limit at 1 is 2. The limit and the function value can be the same and they can be different. In this case, they just happen to be the same thing. So this function actually gets to 2 from both sides. Now, if this is the case right here, if the limit and the function value are equal, the function must be continuous at 1. It has to be. It approaches the value and it gets there. It's continuous there. The second example, we have a hole in the graph. We have a removable discontinuity, but let's investigate the limits. We have the limit as x approaches 1 from the left. It's approaching 2, but it never gets there. But that's different than a function value. Limit just says, what is it approaching? What is it getting closer to? It's getting closer to 2, the y value. From the right, it's also getting closer to a y value of 2. And believe it or not, the limit is 2 because those two equal each other. It's approaching the exact same value, so it has a limit there. But the function value it doesn't exist. So that's an example of where the limit and the function are really two different things. They can be the same, but not always. This is an example of there's a discontinuity there. What it's approaching and what it actually is two different things. The third example is, of course, a jump discontinuity. So we have a limit as x approaches 1 from the left. Now that's on the left-hand side from the left. The limit is 1, even though it never gets there. There's a hole in the graph there. It never gets there, but that's what it's getting closer to. Limit as x approaches 1 from the right is up here at 3. So the limit doesn't exist. It can't be two different values at that x value. It's either equal or not equal. If it's not equal, it doesn't exist. The function value exists. It's up here at 3. So because those are different, there must be a discontinuity there. We can tell by the graph, but what if we didn't have the graph? We would at least know there's a discontinuity there. Then on the last one, we have 2, 2, and 2. It's approaching 2 from both sides, so the limit must be 2, but the function value is up there at 4. So they both exist, they're different, so there must be some kind of discontinuity going on there, and it's a removable discontinuity as well. So I've described limits, described kind of how you say limits. Limit as x approaches something of some function. But down in the end there where I said compare the two, that is called the continuity test. The limit as x approaches some value of f of x must equal f of a. So what the function is approaching and what the function value actually is, if it's the same, it's continuous there. It has to be. What if we didn't have a graph? We're going to use the continuity test to decide whether it's continuous there. Determine whether that function is continuous at x equals 2. Justifies using the continuity test. This represents approaching 2 from the right. This represents approaching 2 from the left. And we're going to use our calculator to fill in these values. We're going to go to y equals. We'll turn it on, of course. We're going to go to y equals. That's in the top left. And we have 2x squared minus 3x minus 1. And press enter so that it kind of enters there and there. We're going to go to the table set. We're going to use a table to do this. And yours probably says 0. That's exactly what it looks like if you've never gone in here and changed things. Well, this says start at 0, change your values by 1, and do it automatically. Well, our values aren't changing by 1. From 2 to 2.001 is not 1. It's 0.001, but then the next one only changes by 0.01. So it's not the same. It's not nice. So we're just going to have the calculator ask us, just the first one, it's going to ask us, well, what do you want me to evaluate, instead of doing it automatically. Then you go second, and you want table up here at the top right, table up here, and the table's blank. If I had it on auto, it'd be filled in automatically. Well, now I'm going to evaluate 1.9, and we're using that function that we put into y1. So 1.9 is 0.52. 1.99 is 0.95. 1.999 is 0.995. So do you get a sense of what we're approaching? What value are we approaching as we get closer to 2? What do you think? 1, right? Looks like we're getting closer to 1. Now how about on the right-hand side? 2.1, 1.52. 2.01, 1.05, and 2.001, 1.005. So what do you think it's approaching from the right? 1, right, as well? What kind of discontinuity could we still have? We could still have a hole in the graph, which is removable. We could still have a hole there. That's a possibility. But since we're using the test, we got to make the statement, limit as x approaches 2 of f of x seems to be 1. The evidence points to the fact that it's probably 1. Now we got to look at the function value, and so we just have to plug 2 in. Plug 2 in. Oh, it's actually 1. So f of 2 is equal to 1. That means this must be continuous at x equals 2. It has to be. The limit and the function value equal each other. What the graph is approaching is the same as where it is. Determine whether each function is continuous at x equals 0. Justify using the continuity test. So I'm going to show you how you would do this with a piecewise function rather than that polynomial. So this is an example of what you're going to do in your homework. You're going to make that chart, but you're not going to do 3 values. I thought 2 values on each side would be plenty. So how about 0.001 and 0.01, and negative 0.001 and negative 0.01. This function, these aren't very long, so I don't think I'd plug these into y1. I think I would just do all of this from the home screen because it's just not that long of an equation. If I'm to the left of 0, I'll use 1 over x. So 1 divided by negative 0.01. Negative 100. 1 divided by negative 0.001. Negative 1,000. What's going on here? Any ideas? What if I plugged in 1 divided by negative 0.0001? Whoops, I missed 1 0. There we go. What do you think that's going to say? Negative 10,000. What if I add another 0? It's going to be negative 100,000. It's going down to negative infinity. We have an infinite discontinuity here. Because the closer I get to 0 on the left-hand side, the more negative it gets. It's just shooting down to negative infinity. So this limit, the left-hand limit, seems to be going down to negative infinity. So if I were to graph this, I'm guessing that right at 0, it's doing that action right there. All right, how about the right-hand side? It doesn't really matter now. Even if the right-hand side is negative infinity, the limit doesn't exist. But let's complete the problem. If you're on the right-hand side, you're just using x. So that's easy enough. I don't even need a calculator for that. So on the right-hand side, the graph looks like y equals x. So it should be a straight line. It's approaching 0 on the right. So this is approaching 0. But here's what we get out of this. The limit as x approaches 0 of f of x does not exist. But to complete the test, f of 0 equals 0. There's the test. I need those two statements right there. What is the limit and what is the function value? Now I know I already knew right here that there is an infinite discontinuity at x equals 0. Because the closer I got, just the more negative it's going to get. Determine whether each function is continuous at the given x value. Justify using the continuity test. If discontinuous, now identify the type. I don't think I did before. Oh, I did. I didn't need to, though. It wasn't in the instructions, so that was some extra answer. All right, we're at negative 3. Away we go. Tedious. I get it. This is tedious, but this is what I want. I got to get close to the left. That would be negative 2.999. I mean right, not left. Negative 2.99. And how about negative 3.001, negative 3.01? Now you got to decide, are you going to use the function and the chart, or are we just going to plug them in? I think 3x minus 2, not that bad. I don't feel I need to use y1 for this. To the right of negative 3, we use the top. 3 times negative 2.99 minus 2. Negative 10.97. 3 times negative 2.999 minus 2. Negative 10.997. Do you get a sense of what it's probably approaching? Probably what? Negative 11, right? Probably negative 11. So I think the right-handed limit is negative 11. How about the other side? If we're less than negative 3, we're using 2 minus x. And 2 minus negative 3.01 is negative 5.01. This is negative 5.001. So I get the sense that this is approaching negative 5 on the left. The limit as x approaches negative 3 of f of x does not exist. But what kind of discontinuity do we have here? Can you visualize it a little bit? If one side is approaching negative 5 and the other side is approaching negative 11, jump. The jump discontinuity. But we got to finish the test. F of negative 3 is equal to 2 minus negative 3 is 5. So the solid dot happens to be on the left branch. So we have a jump discontinuity at x equals -3. The right and left-hand limit are not going the same thing. Go ahead. Oh, oh yeah, 5. Oh, this should be positive, shouldn't it? I'm sorry. Right? 2 minus negative. That should be positive, not negative. So then, oh, where did I get that right there? Yeah. When I plug that in for that, 2 minus -3 is +5. The actual function value. Those should have been positives, not negatives. All right. One more example of this. Tedious, I know, I get it. It's tedious, but we got to do it. That's what I want. This one's a lot to enter for a whole bunch of values, so we're going to go back to y equals. We're going to use the calculator for this one, or the table. X plus 3 divided by x squared minus 9. And you got to have those parentheses in there, or you're going to get some wrong values. You paid for all the keys, you might as well use them all. If you don't like the clutter from the last one, you can delete all these out. Just keep hitting delete, and it just kind of automatically deletes them all out. Our first value we're going to look at is -3. So -2.999, -2.99, -3.01, -3.001. Oh, those are backwards. Oh. -2.99. There we go. That's better. -3.01. Enter. -0.1664, I think it is. And then -3. Whoops, I missed the 3. 3.001. -0.1666. This is approaching -0.1666. Keep on going. Sometimes the chart is bad in that it doesn't go out to very many decimal places. But once you get the hang of this, I think you'll realize what's happening pretty quickly. -2.99. -0.1669. And -2.999. So -0.1667. So I feel like the right-handed limit is exactly the same thing. That's what I feel both of them are. So the limit as x approaches -3 of f of x is equal to -0.1666. Keep repeating. There's a fraction associated with that, and there's a way to get it, but that's for another day. Now to finish it up, we need f of -3. There still could be a removable discontinuity here, or it could just be continuous, because the limit's good. We got a good limit. Now do we get a good function value? Well, -3 plus 3 is 0. -3 squared is 9. 9 minus 9 is 0. 0 divided by 0 is not 1. It's undefined. So the function value doesn't exist. So we must have a removable discontinuity, I should say discontinuity, at x equals -3. Limit's good. It's going to a value on both sides. But once we get there, there's nothing there. There's a hole in the graph. All right, last one here, and we're moving on. 3. 3.001. 3.01. 2.999 maybe. 2.99. Get really close. Limits, when you're approaching a value, when you're doing a limit, you're not approaching from 2 miles away, because too much can happen. You're approaching very close to the point. That's how you approach a value. 3.01. 100. 3.001. 1,000. We've seen this before. What is that approaching? Infinity. It's going up. Closer it gets to 3, the higher it's going. So we have a vertical asymptote here. We have an infinite discontinuity. I'm kind of done with this one, but we want to finish the problem. I want to see a complete problem. So 2.999, what's happening on the other side? This one's going down to negative infinity. So 2.99, negative 100. So this is approaching negative infinity. This is approaching positive infinity. So at 3, 1, 2, 3, I know that this is happening right here. It's going down like that, and the graph must be going up like that. That's what's going on with the graph. The limit as x approaches infinity, no, 3, sorry. Limit as x approaches 3 at infinity on the mind there is equal to does not exist. And even if this is the situation where at 3, if it was going up to infinity on the left and up to infinity on the right, the limit doesn't exist. Infinity doesn't exist either, so the limit doesn't exist, even if it's the same thing. As long as it's at 1's infinity, done. F of 3 equals 6 over 0, because 3 plus 3 is 6. 9 minus 9 is 0. Neither one exists. There, I've completed the continuity test. Infinite discontinuity at x equals 3. This will go much quicker than it takes to explain it. This won't take you very long. Any questions? All right. Something a little different. The intermediate value theorem says if you have A, B here, and you have f of A and f of B, so you have the x's and the y's. And if you had these points right here, at a f of A and b f of B, if the function is continuous, the function takes on all of the y values between f of A and f of B. Now that's a generalization, and that's always confusing when we use generalizations. So let's throw some numbers in. What if this was 2 to 6 and the y values were 8 to 15? So we have the point 2, 8 and the point 6, 15. The intermediate value theorem is saying as long as the function is continuous, there's an f of something that equals something between 8 and 15. Let's say 9. Somewhere the function value is 9. And there's an x value that gives us that value of 9. Somewhere. Somehow, some way. As long as the function is continuous. And we could write that instead of 9, we could write anything from 8 to 15, and x value gives that value somewhere. So here's how we use it on example 3. Determine between which two consecutive integers the real zeros of each function are located on the given interval. So where are the zeros? Between what two numbers? That's the question. So let's go back to the calculator. We'll clear y1 out. X to the third minus 4x plus 2. Notice that the intervals between the values, the x values, are all 1s. So now I can go up to table set. I can start at -4. This is on table set, second button. I can start at -4, go by 1s. That's what that means. And just do it automatically, because if you're just going by 1s, I don't need to plug in all these values. I can have the calculator do it. So then we go to table. Notice it starts at -4 and it increases by 1s. So now we can just fill it in. -46, -3, oh no, -13 I meant, 2, 5, 2, -1, 2. And I just have to arrow down to get the couple that are left over here. 17, 50. Now, when you do this in your homework, you don't have to write out this chart. It's unnecessary. Just bring it up on the calculator and answer the question. And the answer is, the question is, where are the zeros? Well, it has to be between here. There's got to be one here. There's got to be one here. Because if the y values go from being negative to positive, somewhere that graph crossed the x-axis. Somewhere in there, The y is 0 if this function is continuous, and it is. So to answer the question, if this was in the homework, I would just look at the calculator and say between -3 and -2, 0 and 1, 1 and 2. You don't have to write that whole chart out, not necessary. All right, hang in there. We're almost done. A little long today. I'm not too worried about this. Don't worry about showing this numerically. Use the graph of that function to describe its end behavior. How does it end? What does it look like on the ends? That's the question. The way we answer this is we do the limit as x approaches infinity of f of x and limit as x approaches -infinity. So what happens, how does this function end as x gets really, really big? And if this is the graph, as x gets really big, y is getting really negative. So this function on the right-hand side is going down to -infinity. That's what the arrow suggests. Then, as we go to the left, as x gets really, really negative, y is also getting really, really negative. So that one's -infinity as well. So if you look at the graph and you notice that both are -infinity, it's okay to write this. You don't have to write all of this, one or the other. You can summarize it in one statement. If they're the same, if they're different, I want two separate statements. So graphs can end either shooting up to positive infinity or down to -infinity. And graphs can also end by leveling off to a value. And that's what's happening here. The right-hand side's leveling off to 0. The left-hand side's leveling off to 0 on this graph. So we can make the statement the limit as x approaches plus or minus infinity of f of x is equal to 0. This graph on both sides is leveling off to 0. We also say that this has a horizontal asymptote because it'll approach 0, but it'll never get there. That's why a limit statement is nice for this, because a limit is what is it approaching, not necessarily where it gets to. Could be, but not in this case.